There lies a mysterious occurrence deep beneath the sands of South Australia. All signs point to a massive dual asteroid impact known as the East and West Warburton craters. It's suspected that a massive asteroid or comet split into two before smashing into Australia, with each leaving behind craters of 200 kilometers in diameter. They are believed to have occurred during the Carboniferous period, between 358.9 to 298.9 million years ago. I made a video on the asteroid impact that exists in New South Wales, which is suspected to be an astonishing 520 kilometers in diameter. You can find a link to that video in the description. Prior to the announcement of this impact crater, the East and West Warburton sites were thought to be the largest impact sites on Earth. The only thing that stopped them from taking first place was the fact that they split in two prior to impact, leaving the Vredefort impact site in South Africa as taking first place prior to the announcement of the impact site in New South Wales. The link to the video that I made on that will also be in the description. The East and West Warburton craters are buried under nearly 4 kilometers worth of sediment. The area where the Warburton impacts occurred was likely covered by extensive swamp forests, rich in primitive plants and inhabited by diverse amphibian and early reptile species. The climate was warm and humid, with periodic marine transgressions influencing the landscape. This biome was very different from the arid and semi-arid conditions seen in much of Australia today. Asteroid impacts the size of the Warburton impacts would have caused significant environmental disruptions, including the release of vast amounts of energy, heat, and potentially triggering volcanic activity. They would have had profound and far-reaching effects on the Earth's environment and ecosystem. The impact would release an immense amount of energy, equivalent to millions of nuclear bombs detonating simultaneously. This would create an explosion with temperatures reaching several thousand degrees Celsius, instantly vaporizing the asteroid and a significant volume of the Earth's crust. The initial impact would form a transient crater, which would quickly collapse to form a larger, more stable crater structure. Central uplift domes would form due to the elastic rebound of the Earth's crust. The impact would generate massive shock waves that would propagate through the Earth, creating widespread earthquakes. These seismic waves could be felt thousands of kilometers away from the impact site. Material ejected from the crater would be thrown into the atmosphere and distributed over a vast area. This debris would include pulverized rocks, minerals, and possibly vaporized asteroid material. Some of the ejecta would re-enter the atmosphere, causing secondary impacts and widespread fires. The ejecta, consisting of dust and aerosols, would enter the atmosphere and block sunlight, leading to a phenomenon known as impact winter. This would result in a significant drop in global temperatures, potentially lasting for months to years. The impact could also cause the release of sulfur dioxide into the atmosphere, leading to the formation of sulfuric acid aerosols and acid rain. The acid rain would have had harmful effects on plant and aquatic ecosystems. The combination of dust blocking sunlight and the release of greenhouse gases from wildfires could lead to complex climate changes. Initially, a period of cooling known as impact winter would be followed by potential global warming due to the increased greenhouse gases. Acid rain and increased carbon dioxide levels could lead to ocean acidification, impacting marine life, particularly organisms with calcium carbonate shells or skeletons. The drastic environmental changes could lead to mass extinctions, particularly affecting species that are unable to adapt to rapid changes in climate, light, and temperature. The End-Ordovician and Cretaceous Paleogene extinctions are examples of mass extinction events linked to asteroid impacts. Over time, the impact craters and the associated geological features could become new habitats for life. Lakes or seas may form in the craters, and the nutrient-rich soils from the impact could foster new plant growth. The dramatic environmental changes would create new evolutionary pressures, potentially leading to rapid evolution and the emergence of new species adapted to the post-impact environment. As a side note, if you enjoy this video, consider liking it to help YouTube promote it to other viewers. If you enjoy this type of content, consider subscribing to the channel and hitting the bell icon to be notified of every time we upload. We also have a Patreon for anyone who has the means to support the channel. The link to this will be in the description and in a pinned comment down below. Seismic and magnetic studies have revealed circular anomalies consistent with large impact craters. These anomalies suggest that the impacts created substantial fracturing and reorganization of the Earth's crust in the region, leading to the formation of deep basins. Similar to the impact in New South Wales and in South Africa, the Warburton impact sites exhibit multiple ring patterns, which are characteristic features of large impact structures. Multiple ring patterns are concentric rings of fractures and faults around the impact site, formed by the immense energy and shock waves generated during the impact event. The magnetic surveys of the Warburton Basins have revealed symmetrical rippling patterns in the crust around the structure's core, indicative of multiple ring structures. These patterns are created by the redistribution of magnetic minerals during the impact, which are a key indicator of high-pressure shock metamorphism typically associated with asteroid impacts. Geophysical modelling of the Warburton Basin has shown significant magnetic and gravity anomalies, supporting the hypothesis of an impact origin. These anomalies align with what is expected from the subsurface structures resulting from such impacts. Core samples from drilling operations have provided direct evidence of the impact structure, including the aforementioned shocked quartz and breccias. These samples help to confirm the impact origin and provide insights into the conditions during and after the impact event. Both the East and West Warburton impact sites exhibit features that suggest the presence of central uplift domes, which are a characteristic of large impact structures. Geophysical studies, including seismic tomography, have revealed low-velocity zones in the crust that are indicative of large-scale impact structures. Low-velocity zones, or LVZs, are regions within the Earth's subsurface where seismic waves travel more slowly than in the surrounding materials. These zones are significant in geophysical studies because they often indicate areas of geological complexity and can provide valuable insights into the subsurface structures and processes. These zones suggest significant fracturing and deformation consistent with the formation of central uplift domes. Magnetic surveys have detected circular patterns and low magnetic zones that align with the presence of central uplift structures. These anomalies reflect a disruption and redistribution of magnetic materials during the impact event. According to studies by Glickson and others, the West Warburton Basin shows a central low magnetic zone, which corresponds to a 30-kilometre deep deformation above a seismically defined mantle dome. The geological features of the Warburton Basin, such as the presence of radial faults and specific magnetic patterns, are similar to other known impact sites with central uplifts, such as the Vredefort and Sudbury impact structures. These similarities strengthen the hypothesis that the Warburton sites also have central uplifts. The impacts that created the East and West Warburton Basins could have influenced the formation and concentration of various mineral deposits. Impact events are known to create conditions favourable for the formation of certain types of mineral deposits through processes such as shock metamorphism, hydrothermal activity, and the creation of breccias. Impact events can create extensive fracture networks and heat sources, leading to the circulation of hydrothermal fluids. These fluids can deposit minerals such as gold and copper in the fractured rocks, and are associated with iron oxide copper-gold deposits. Hydrothermal veins and breccias formed in the wake of the impact might host these valuable minerals. Similar to gold and copper, hydrothermal systems associated with impact structures can also concentrate silver and lead, often found in sulfide minerals such as galena and argentite. The intense heat and fracturing from the impact can mobilize uranium, leading to the formation of uranium deposits. These deposits can form in brecciated zones or along faults created by the impact. If the impacting body contained nickel and platinum group elements, these elements could be introduced into the Earth's crust and concentrated in impact-related deposits. The Sudbury Basin in Canada, which we also made a video on, the link to that will be in the description, is a well-known example of an impact structure that hosts significant nickel and platinum group element deposits. In summary, an asteroid impact the size that formed the Warburton Basins would have caused immediate catastrophic environmental changes, including massive explosions, wildfires, and climate disruptions. These changes would have had long-term effects on the Earth's climate and ecosystems, potentially leading to mass extinctions and significant shifts in the evolutionary trajectory of life on Earth. Studies are still ongoing, as is exploration for mineral enrichment associated with the impacts that could be possible sites for future mines. So this is the story of the cataclysmic East and West Warburton impact sites. Even though they occurred hundreds of millions of years ago, there's nothing stopping an event like this from taking place again on our planet. If it did, it might spell the end of humanity. Thanks for watching. Did the largest impact site known on Earth occur in Australia? As of 2024, it appears as though all signs are pointing to a yes regarding this question. The Deniliquin impact site was announced late last year in 2023, though studies into it began in 2022, and I've been watching closely ever since then. After scouring Google Scholar, we have many signs that an impact with a size of 520 kilometers or 323 miles occurred here. This would make it the largest known impact site on our planet. For comparison, the largest proven impact site occurred in South Africa, with a crater size of 300 kilometers or 165 miles, and we've already released an episode on the Vredefort impact site. The link to that is in the description down below. If the Deniliquin impact site turns out to be true, it would be almost double the size of the ancient impact site in South Africa. That is jaw-dropping to say the least. For further comparison, this is almost 4 times larger than the Chicxulub crater, which wiped out the dinosaurs. This impact site is associated with a period of glaciation known as the Hernantian glaciation event, and if it occurred, it is projected that it eliminated 85% of species on our planet. The date this asteroid is estimated to have made landfall is in the late Ordovician, between 445.2 and 443.8 million years ago. It's worth noting that many of the gold deposits in Victoria were deposited during this time. Is there a relationship between the two? There's actually a strong possibility in this case. It might be why the Bendigo goldfields were so incredibly enriched in comparison to any other area in Victoria. And it also might be why areas around Malagal featured the largest gold nuggets in the world. So in this video, we'll be using magnetics to scour the landscape, and we'll be looking into what forms of evidence currently exists. We'll also explore what it means in terms of mineral deposition. From what I can see, there's an evident central uplift dome, and a multiple ringed feature like what occurs at the Vredefort impact site. It's worth noting that these are rare on Earth, and they usually occur on other planets and moons. The issue? This proposed impact site is buried deeply beneath the recent sediments of the Cenozoic-aged Murray Basin. So far, drill cores have failed to intercept any shocked quartz, shatter cones, and other impact-related phenomenon, which are telltale signs of major impact events. This doesn't mean the asteroid didn't impact here. On the contrary, it means we need to drill deeper. Unsurprisingly, the proposed impact site takes its name from the town of Deniliquin, which is where the central uplift dome appears to be. I will show you this in a moment, but before I do, it's worth mentioning that post-impact, Silurian-aged magmatic intrusives occurred here, depositing granites into the crust. The Silurian occurred after the late Ordovician, and spanned between 443.8 million years ago to 419.2 million years ago, and these granites might be associated with the impact event. On the magnetics, we have a feature that appears to be the central uplift dome, followed by radial rings all around the site. There are also radial fault lines. The proposed impact was certainly huge in its scale, with a possibility that it stretched from an area just past Mildura all the way to Wagga Wagga, and it affected areas in northern Victoria too, including the famed goldfields, with a possibility that it extended all the way down south to Sunbury. On a side note, if you like this content, please hit the like button to help YouTube promote the video. We also have a Patreon if you would like to support this channel. The link to this will be in the comment section and in the description down below. Now back to the cataclysm. Extreme glaciation and an extinction event where approximately 85% of all Ordovician species died occurred around the time the Deniliquin impact site is dated. Widespread glaciations and a drop in sea level of about 80 meters persisted into the early Silurian. It's very possible that this is the reason for such pronounced effects on Earth. The Deniliquin impact site is buried by at least 300 meters of recent sediments. It doesn't appear to outcrop anywhere, and it is assumed to be a deeply seated site. This impact has remained hidden for a long time due to the fact that the area where it occurred underwent a tectonic event known as an orocline. An orocline is a geological term used to describe a large-scale bend or curvature in a mountain belt or orogenic belt. This bending usually occurs after the initial formation of the mountains, and it often results in a noticeable change in the orientation of the structures within the belt. Oroclines are typically associated with tectonic processes, such as collision and subsequent rotation of tectonic plates, which can cause the original linear mountain ranges to buckle and bend. This happened in northern Victoria and southern New South Wales. The orocline in Victoria to southern New South Wales, specifically the Lachlan orocline, formed during the Silurian to Devonian periods. This large-scale bending and reorientation of the Lachlan fold belt occurred approximately 440 to 400 million years ago. Did this impact site contribute something to this orocline? Whilst this question currently remains unanswered, it's definitely something to consider. So what would have happened when this impact occurred? Well, the Earth would have turned into a hellscape. Firstly, it would have carved through the bedrock and produced a massive cauldron of molten material. When asteroids impact the Earth, a rebound effect occurs in the centre of the impact site, leaving behind a central uplift dome. It would have created violent mega tsunamis, and it would have produced the largest earthquakes known to man. A quake so powerful it would have been felt in every part of the planet. When it impacted, it would have ejected vast amounts of material into the atmosphere, only for it to rain down as fiery debris-laden balls of sedimentary hell. It would have raised the temperature of the atmosphere to unthinkable levels, and the ejector released would have shrouded the globe for an unthinkable amount of time. This is why it's linked to producing the Hernantian glaciation event, as it would have blocked incoming sunlight and plunged the temperatures of the Earth by a drastic amount. While studies are preliminary, it is agreed that we need to drill much deeper to attempt to intersect the proposed impact site. If we find anomalies in the rock like shocked quartz and shatter cones, this would fully confirm that this event occurred. But there's a chance the mid to upper levels of metamorphosed rocks have been eroded, and there's also the possibility for deep mineralization, as it would have turned a land into a molten crater, melting and sequestering gold, copper, silver and other valuable commodities that existed in the crust at that time. Due to the heavy specific gravity, these would have sunk to the lowest depths of the impact site. The Vredefort impact site in South Africa is one of the most gold-saturated places to have ever been discovered. The gold lies within conglomerates inside the impact site. A similar thing may exist in this part of Australia. But what do you think? Do you think this was a major asteroid impact, or are the features in the land merely a part of the many tectonic events that Eastern Australia underwent from the Cambrian onwards? Let me know in the comments. And as always, thanks for watching. In the centre of the Australian continent exists a very strange magnetic anomaly that stands out amidst the region. This is the story of Mapsus, the massive Australian Precambrian to Cambrian impact structure, a hypothesised impact crater that could be among the largest known on Earth. It's speculated that a 600 km wide crater exists from a massive asteroid that slammed into the Centralian superbasin at some point in the Precambrian to Cambrian era. If confirmed, Mapsus would not only be a remarkable geological feature, but also a crucial piece in the puzzle of the Precambrian to Cambrian transition, a period marked by profound environmental and biological changes. When the asteroid that created the Mapsus impact structure struck Earth, it did so from a dramatic and oblique angle, carving a path of destruction across the ancient landscape of what is now Central Australia. Unlike a vertical impact, where the asteroid would plunge directly downwards, an oblique impact involves the asteroid hitting the surface at a lower angle, more like a skipping stone across water. This kind of impact produces distinctive geological features, and has far-reaching implications for the environment. The journey to uncover Mapsus began with a series of geophysical anomalies detected in Central Australia. Researchers noticed a pronounced circular gravity anomaly, which suggested the presence of a large buried structure. Further investigation revealed an extensive pseudo-tachyllite breccia deposit in the Musgrave Block, located on the southern flank of what would later be identified as the Mapsus structure. Pseudo-tachyllite breccia is a type of rock typically formed under extreme pressure and temperature, conditions that are often associated with meteorite impacts. Mapsus is proposed to be a peak ring crater, a type of impact structure characterised by a central uplift surrounded by a ring of mountains or highlands. The estimated diameter of Mapsus is approximately 600 kilometres, making it larger than some of the largest known impact structures on Earth, such as the Vredefort crater in South Africa and the Sudbury Basin in Canada, both of which I've made a video on. You can find a link to these videos in the description below. The structure is slightly oval in shape, with its long axis orientated east to west, and is centred in the heart of Australia's outback. The evidence supporting Mapsus as an impact structure is compelling. The Musgrave Block, where the pseudo-tachyllite breccia is found, provides some of the most significant clues. This breccia extends for over 300 kilometres, and can be up to 5 kilometres wide. It is strikingly similar to pseudotachelite found in other confirmed impact sites, reinforcing the idea that Mapsus is indeed the result of a massive extraterrestrial collision. Further supporting the impact hypothesis is the discovery of lonsdaleite, a rare hexagonal form of diamond that is typically associated with meteorite impacts. Lonsdaleite forms under the extreme pressure and temperature conditions created when a meteorite strikes the Earth. Raman spectroscopic analysis of samples from the Musgrave block confirmed the presence of lonsdaleite, adding to the growing body of evidence that Mapsus is an impact structure. One of the most intriguing pieces of evidence for Mapsus's impact origin is the detection of high concentrations of iridium within the pseudotachelite breccia. Iridium is a rare element on the Earth's surface, but is more common in meteorites, making it a key indicator of extraterrestrial impacts. The levels of iridium found at Mapsus are several orders of magnitude higher than what would be expected in the continental crust, suggesting an impact source. The iridium anomaly is not unique to Mapsus. Similar anomalies have been found at the pre-Cambrian to Cambrian boundary in other parts of the world, including China, Russia, and Tasmania. The discovery of iridium at Mapsus could help to link these global anomalies and provide a more comprehensive understanding of the events that occurred during this pivotal period in Earth's history. Mapsus's potential significance extends beyond its immediate geological features. There is a hypothesized connection between Mapsus and the Kolkarinji Large Igneous Province, a massive volcanic event that occurred around the same time as the proposed impact. The Kolkarinji Large Igneous Province is a large volcanic province on Earth, and its eruption may have been triggered or influenced by the impact that created Mapsus. The Kolkarinji Large Igneous Province represents one of the major volcanic events in Earth's history, occurring approximately 510 to 500 million years ago, during the early Cambrian period. Covering an area of about 2 to 3 million square kilometres across northern Australia, this large igneous province is characterised by extensive flood basalt eruptions. These volcanic activities released vast amounts of lava and gases, potentially leading to significant environmental disruptions, including climate change and ocean anoxia. The scale and intensity of the Kolkarinji Large Igneous Province make it one of the more prominent geological features of the Phanerozoic Eon, and its timing coincides with critical biological changes during the Cambrian explosion, a period marked by the rapid diversification of life on Earth. The relationship between the Kolkarinji Large Igneous Province and the Cambrian explosion has intrigued scientists, as the environmental impacts of such a large volcanic event could have played a role in shaping early animal life. The emissions of sulfur dioxide and other volcanic gases would have likely led to acid rain, ocean acidification, and a drop in global temperatures, creating challenging conditions for existing species. These harsh conditions might have driven evolutionary pressures that contributed to the rapid emergence of new life forms during the Cambrian period. This connection raises the possibility that the impact could have had far-reaching effects, not only causing local devastation, but also triggering volcanic activity and influencing tectonic processes. The spatial and temporal correlation between Mapsus and the Kolkarinji Large Igneous Province suggests that the impact may have played a role in the rifting between the North Australian Craton and the South Australian Craton, potentially stimulating plate tectonics in the region. If confirmed, Mapsus would be a monumental discovery, with profound implications for our understanding of the Earth's history. The Precambrian to Cambrian transition, marked by the Cambrian explosion, was a time of rapid evolutionary change, with the sudden appearance of many major groups of animals. An impact of the scale suggested by Mapsus could have been a catalyst for these changes, contributing to environmental shifts and mass extinctions. The discovery of lonsdaleite and the high iridium concentrations at Mapsus provides a unique opportunity to study the effects of large-scale impacts on Earth's geology and biology. These findings could help shed light on the role of impacts in shaping the planet's surface and influencing the course of evolution. Previously, the Deniliquin structure in New South Wales was thought to possibly be the largest impact structure on Earth, with it featuring a 520 km diameter crater. I made a video on that, and you can find a link to it in the description below. If Mapsus turns out to be an impact site, it would take the throne as being the largest known impact site on the planet, meaning Australia would have two of the largest known craters in the world. Mapsus is a fascinating and potentially transformative discovery. The evidence gathered so far strongly supports the hypothesis that it is an impact structure, and further research could confirm its place as one of the largest known impact sites on Earth. The implications of Mapsus are far-reaching, offering new insights into the Precambrian-Cambrian transition, the interplay between impacts and volcanic activity, and the forces that have shaped our planet's history. As research continues, Mapsus promises to be a key piece in the puzzle of Earth's early history, revealing the dramatic events that have shaped the world we live in today. Whether it ultimately proves to be the smoking gun behind a Cambrian explosion or a driving force behind ancient tectonic shifts, Mapsus is a discovery that could change our understanding of the deep past forever. Thanks for watching. Within the remote Kimberley Plateau of Western Australia lies one of the most fascinating and complex geological structures on Earth, the Spider impact structure. This fascinating formation, with its distinctive radiating faults that give it the name Spider, is a truly unique looking impact crater. The Spider impact structure was first identified in the mid-20th century, though its true nature remained unclear for some time. Between 1953 and 1957, during the geological mapping of the Kimberley region, geologists noticed an unusual circular formation in aerial photographs. Initially, the structure was ambiguously marked on maps with the annotation glacial structure with a question mark due to the nearby exposure of tillite, a type of sedimentary rock formed from glacial debris. It wasn't until later, in the 1970s, that the structure began to attract serious attention. Originally, it was suggested that it could be a diatreme, a volcanic pipe formed by explosive volcanic activity. This hypothesis led to further fieldwork, including visits by researchers from BHP in 1977. The discovery of shatter cones, distinctive conical fractures in rock that are typically associated with impact events, provided the first strong evidence that the Spider structure was not volcanic, but rather the result of a meteorite impact. In the years that followed, further investigations, including remote sensing, geological mapping, and the use of satellite data, solidified the understanding that the Spider structure was indeed an impact crater, albeit one that had undergone significant erosion and deformation over the eons. The Spider impact structure is located approximately 8 km west of the Han River, on the south-central Kimberley Plateau. The structure itself is approximately 13 km by 11 km in size, or 8 by 6.8 miles. With its central region dominated by a unique system of radiating thrust faults that extend outward from a central sandstone dome. This pattern of faults, which resembles the legs of a spider, is what gives the structure its name. The geology of the Spider impact structure is complex and multi-layered, reflecting the various stages of its formation and the subsequent geological processes that have shaped it. The target rocks at the impact site are primarily shallow marine sandstone and siltstone, deposited during the Paleoproterozoic era in what is now the Kimberley Basin. The oldest rock unit exposed within the structure is the Warburton sandstone, a mature, medium-grained arenite that may be up to 500 meters thick in some areas. This sandstone is overlain by the algae siltstone, a succession of siltstone and mudstone with interbedded sandstone layers, and then by the Pentecost sandstone, which is a mature quartzitic arenite. The entire sequence of rock units has been deeply deformed by the impact event and subsequent tectonic forces. One of the most striking features of the Spider structure is its central uplift, a dome of Warburton sandstone that rises above the surrounding terrain. This uplift was formed during the impact event, as the immense energy of the collision caused the rock layers at the centre of the impact site to rebound and push upward. Surrounding this central dome is a system of imbricated thrust sheets. Imbricated thrust sheets are overlapping slices of rock layers that have been pushed over one another along thrust faults, typically forming during compressional tectonic events or impact-induced deformation. The Spider legs, which radiate outward from the centre, do so in a bilaterally symmetrical pattern. As a side note, if you're enjoying this video, please click the like button to help YouTube recommend it to others. Consider subscribing and clicking the bell icon to be notified of when we upload. We also have a Patreon if you'd like to support the channel, only if you have the means of course, and you can find that both in the description and in the pinned comment down below. When geologists first began exploring the Spider structure in detail, they were struck by the presence of a peculiar and fascinating feature, shatter cones. These cone-shaped fractures, which can extend over 1 meter in length, were found embedded in the quartzite rocks of the central dome and surrounding thrust sheets. Unlike any other geological formation, shatter cones are a unique and telltale sign of an impact event, formed under the extreme pressure and shock of a meteorite collision. The discovery of these shadow cones at the spider structure was a significant breakthrough. Their distinctive conical patterns, which fan out from a central point like the flaring of a jet, told a story of unimaginable forces at work. The intense shockwave generated by the meteorite impact had passed through the rock, fracturing it in a way that only a violent event could produce. For the geologists studying Spider, these shadow cones were a definitive piece of evidence, an irrefutable marker that this remote area had once been ground zero for a cosmic collision. As the investigations continued, the story of the Spider impact structure grew even more compelling. In addition to the shadow cones, another crucial piece of evidence emerged: shocked quartz. This rare and microscopic feature is created only under the intense pressures and temperatures of an impact event. The quartz crystals in the spider structure bore the telltale signs of planar deformation features, tiny parallel lines within the crystal structure that can only form under the extreme conditions of an impact. The breccia at the spider impact structure is a crucial indicator of the intense forces generated by the meteorite impact that created the structure. Formed primarily within the imbricated thrust sheets and central dome, this breccia consists of shattered rock fragments cemented together by the extreme pressures and temperatures of the collision. As the meteorite struck, it fractured the local sandstone into chaotic pieces, which were then reassembled into breccia by the heat and force of the impact. The presence of this breccia, along with other impact indicators like shattered cones and shocked quartz, provides clear evidence of the violent processes that shape the spider structure, and confirms its origin as an impact crater. The formation of the spider impact structure is believed to have been the result of a moderately oblique impact by a meteorite or asteroid, with an angle of impact estimated to be between 10 and 30 degrees from the horizontal. The impactor likely approached from the north and struck the Earth at a high speed, releasing an enormous amount of energy in an instant. Upon impact, the kinetic energy of the meteorite was converted into heat and pressure, causing the target rocks to behave like a fluid for a brief moment. This led to the formation of a transient crater, which was much larger than the final structure. The central uplift, or dome, formed as the rocks at the centre of the crater rebounded upwards in response to the impact, while the surrounding material collapsed inward, creating the imbricated thrust sheets. The unique radial pattern of faults observed in the spider structure is thought to be the result of both the oblique nature of the impact and the pre-existing geological conditions at the site. The structure lies across the axis of the Mount Barnett syncline, a broad east to west orientated fault in the Earth's crust. The presence of this syncline likely influenced the formation and orientation of the faults during the impact event, contributing to the asymmetrical deformation observed today. To clarify, a syncline is a type of fold in rock layers where the strata dip inward towards a central axis, forming a trowel-like structure. The spider impact structure is not only a breathtaking geological formation, but it also provides valuable clues into the processes of impact cratering and the deformation of the Earth's crust. The well-preserved and visible radial faults, or spider legs, are the most fascinating part of this impact structure. Whilst radial faults are commonly formed during asteroid collisions, the obvious and visible ones at this crater give it a unique look that isn't seen, to my knowledge, in any other impact crater on the planet. If you watched the last video I made on the possible undocumented impact crater in Western Australia, you'll also find an array of radial faults there. This is also seen in the spider crater, giving it more of a possibility that it is indeed an undocumented crater. I'll leave the link to this video in the description. Furthermore, the spider structure offers clues about the history of the Kimberley Plateau and the broader region. The impact event is estimated to have occurred between 900 million and 610 million years ago, during a period of significant tectonic activity. This timing is constrained by the Yampi orogeny, a major mountain building event that affected the region around 900 million years ago, and a deposition of the Walsh Tillite, around 610 million years ago, when this region was covered by glaciers. The impact occurred before these ice sheets had formed. When this event took place, the impact likely occurred in an already existing syncline, suggesting that the region had undergone significant tectonic deformation prior to the impact event. The deep erosion of the spider structure, which has exposed the central uplift and removed much of the original crater, further indicates that the Kimberley Plateau has experienced considerable geological change over the past several hundred million years. Despite the extensive research that has been conducted on the spider impact structure, many questions remain unanswered. The exact age of the impact, the details of the impactor itself, and the precise sequence of events during the formation of the structure are still subjects of active investigation. High-resolution geophysical surveys and drilling could provide more detailed information about the subsurface structure of Spider and help to resolve some of these uncertainties. Additionally, the Spider impact structure serves as a natural laboratory for the study of impact cratering processes, particularly in sedimentary rock targets. The knowledge gained from studying the Spider crater can be applied to other impact structures around the world, as well as the impact cratering processes on other planetary bodies. Whilst it's highly inaccessible, the Spider impact structure is perhaps one of the most fascinating craters to have ever been found. I've never seen anything quite like it in my years of nerding out over impact craters. It truly is a unique and remarkable structure. I hope you enjoyed this video on this captivating impact site. I'll put a link in the description as always to the papers used to construct this video. Consider subscribing if you'd like to see more videos like this one, as I have a whole list of craters that I intend to cover in future videos. Thanks for watching. Are you interested in animals? I've just started a second channel called Paleozoology that discusses extinct and extant animals with a current focus on the megafauna that once dominated and roamed Australia. I've released a video on the marsupial lion which existed in Australia during the time Indigenous Australians walked the continent. I've also covered the wombat that was the size of a car, known as the Diprotodon, or the largest terrestrial lizard known as the Megalania. I'd love to have you along for the journey as more videos are released. You can find a link to this channel and to the aforementioned videos in the description and in the pinned comment in the comment section. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.